Welcome to today's video. Today we're going to delve a little bit deeper on the differential calculus in a manifold. We're going to learn about delve a little bit deeper into one forms. We're going to learn about nforms. We're going to learn about integrals a little bit. You will do more of that on assignment, but we're going to learn a little bit about integrals. And we're going to learn about exterior products and exterior derivatives. Now, all these concepts are meant to generalize integral calculus to the manifold, and you have used them already. And it's super interesting because in things like in thermodynamics, you probably realize that in thermodynamics you've seen things like this. Differential of internal energy equals, and then depending on your sign convention, let's see, let's write it like this. You would have probably written dq minus dw, right? And like with this, with this line crossing out the d's there. So when you've seen these things in thermodynamics, this is kind of like how physicists try to make sense of notions that require knowledge of differential geometry without actually invoking that much differential geometry. You know what this responds to? This crossed out d, which is arguably a bad notation. It's because physicists are not really used to writing an integral with something that is not d something inside. So writing an integral of just an f probably feels funny, or an omega probably feels funny to a physicist, and it shouldn't be. All right, so let's see what we can do, and let's see what it means to integrate a form. But let's start step by step. Okay, let's erase this for a sec, and let's recall what we saw in the previous video. Now, a one form, of course, you can write as a linear combination of elements of the dual basis to the basis of vectors, of tangent vectors. And also we know that in a coordinate basis, the same way that the partial derivatives were a basis for the tangent vectors, we know that the differentials of the coordinates are basis for the cotangent vector space for the one forms. We also saw a particular one form, that is the differential of a function, given a function f. Remember, f takes, this is the manifold, right? And this is Rn. F is a function that takes points in the manifold and map them to R, right? It returns a real number. We know, given a function, we can build the differential of that function, which is a one form, whose components are precisely the partial derivatives of the function. Well, of the function mapped through phi to a function from Rn to R. Remember that f is the abstract object, and f bar is the object that we actually know how to use through the translation that this map phi, part of an atlas, gives me to translate things in my bag of infinite potatoes to Rn. So the partial derivatives of f bar are what you have used all your life in calculus, right? So we see that the differential of a function is certainly partial derivatives, dx mu, the differential of the coordinates, and this is exactly the expression that you saw in calculus for the differential of a function. But also, you remember this understood as a covector, right? This is a covector, and this is a sum of components times elements of the basis. The components of these covectors, what are they? Well, it's partial f bar, partial x1, partial f bar, partial x2, and that is what you would call the gradient. So certainly the differential of a function is the gradient. The gradient is a covector. It's a one form. All right, we learned all that. Okay, let me erase this, and let's focus now on something new. We're gonna learn how to integrate. Integrate a one form. So imagine that I have a curve, gamma of s, that goes from s1 to s2, like that. S is a parameter that I use to parameterize the curve. It tells me how I move along the curve as I increase s. You can think number of steps, time, or whatever you want. All right, so what is the value? Can I define the integral of a one form along the curve? And yes, I can. You have done that in previous courses. For example, in thermodynamics, you had integrated du from one point to another in a process. So you have integrated even this thing, d/w, right? The amount of work that you do, right, integrating this thing, you've done that in thermodynamics. Well, what is the generalization to that to general manifolds? Let's see. How do I define the integral of a one form omega, a one form field that is defined in all points in the manifold, along the curve gamma? Well, I write it like that, and this is the integral of omega, a one form field, along the curve gamma, and then I just write omega in terms of the coordinate basis, the x mu, one coordinate basis. And then I say, right, but I want to integrate this one-form field. Remember that this thing is a function of the point because it's the component of a one-form field. And I say, well, but I want to sum, in a way, I want to integrate over all points in the curve. So it's not about, I don't want to integrate over all possible x mu, only the x mu that you actually cover when you go around the curve, right? Okay, cool. So then what I do is I parameterize this in terms of the parameter s. So I know, of course, that dx mu is equal to dx mu ds, right? ds, that's the parameterization. Okay, so I write this parameterization here, and then I know now moving around the curve. In this parameterization, it's already fixed because I restricted, remember, I restricted dx mu to be on the curve, and then along that restriction, the integral is just an integral from s1 to s2. And I can just abbreviate this as x. Maybe instead of dot, I should write circle, right? Just to make sure that we won't confuse this with something like proper time or affine parameter that will come later or anything like that. Right. So notice that this is independent of the parameter that I use. Imagine that I now define a new parameter, I don't know, tau equals 2s. Okay, cool. Can I write the integral like that? Sure. So all that I need to do is reparameterize in terms of tau. So I do integral from tau 1 to tau 2 omega mu dx mu d tau, right? D tau. You see, it's the same thing because, again, if you want to use your dirty math, you physicists, I'm a physicist too, so don't worry too much. You can say, right, it's independent parameter. Whatever the parameter you put here, it will not affect the integral. It's this one, after all, right? Restricted to the curve. All right, only that this, of course, is twice the value of S1, right? So that would be equal to 2S1, you know. All right, but you know what I mean. This is independent of the parameter that I use to parameterize the curve. So the value of the integral along the curve, the sum of the contribution of the one form along the curve, does not depend on how fast I walk the curve. I sum it, I take a step, what's the value? This one, okay, add up. Take a step, what's the value? This one, okay, add up. If I do it faster, which is increasing the parameter to twice the speed, I still go along the curve and I still sum everything. So it's parameter independent. All right, so interesting enough, if my one form happens to be the differential of a function, then the integral of the differential of a function is going to be the function evaluated at the end of the curve of the path that I'm integrating over minus the value of the function at the beginning. And I can write a bar or a non-bar because it's the same value. You see, I mean, at every point, either if I go from this point to this point or from this point to this point, I get the same value exactly. This is something that is not unfamiliar to you. You know that when you have the integral of along a curve from S1 to S2 of a df, right, you know that this will not depend on the path, will depend only on f evaluated at the end point minus f evaluated at the beginning point. That's kind of the idea that's coming here. So if my one form is the differential of a function, I know the integral of the one form along the path is path independent. It only, no matter what path I follow, that curve or another curve, if I go through another curve, gamma prime, I'm gonna get the same result if I start and end at the same points, because it's the differential of a function. And we recover something like the fundamental theorem of calculus, differentiable manifold version. All right, but this is kind of cool, because notice that this integral does not depend on what coordinate basis I use. It will be the same for all coordinate bases, the value of this integral, and does not depend on the parameterization of the curve, both for differential of a function and for an arbitrary one form, right? This is just a way to calculate it, if you want, in an arbitrary coordinate basis, but the integral is coordinate independent, coordinate basis independent, and parameterization independent. Now you know how to do the integral of a one form along a path. You've seen this before. That probably you have seen in your calculus, something like the gradient dotted with the velocity of the position in the curve that are moving through the trajectory, and integrated with respect to time from time t1, t2. You've probably seen this in previous courses in physics. You also now probably see the connection, and we will see more as we go, between when you were integrating du, right, an integral in thermodynamics, when you take an integral between 2 points of the internal energy is a state function, and the differential du is that one form that is du is the differential of that function, so only depends on the initial and the final point. But that's not true for work and for heat. Different paths will have different values of heat and work, right? Oh, maybe it's related with the fact that this if you once crossed out differential of Q, that thing is not the differential of any functions. We'll learn more about that in a second. Alright, so next thing. Alright, so you know now that we can integrate one forms. Maybe that wasn't too surprising the moment I wrote that a one form, when I write in a coordinate basis, I can write as the components contracting in terms of the elements of the basis, and the elements of the basis are the differentials of the coordinates. So the moment you see a differential, it's like, oh, can I integrate that? So yes, you can. And maybe now you're not so surprised that I can write integral of omega being a one form. I don't need to write the d because this is already a differential in a way, right? So the fact that you can integrate one forms maybe is not that surprising. And I hope that the physicists in the room are not that bothered by the fact that you can write an integral without a d in it. We need to get past that kindergarten level, if you want, of the notion of integration. All right, kindergarten quotes and quotes, of course. I don't mean that kindergarten kids are going to be able to integrate. Who knows? There are very intelligent babies around, so I don't know. So what are two forms? Two forms are antisymmetric twice covariant tensors. So a 0,2 type tensor that is antisymmetric. What does that mean? Well, sigma being a two form means that it takes, remember what a tensor is, a bilinear in this case because it's twice covariant. Bilinear map that takes two vectors, two vector fields if you want, and returns a scalar. Now, this two, with the fact that it's antisymmetric, I can write as well this acting on VW is minus sigma acting on WV. So it's an antisymmetric one. What does that mean? Well, if I compute the components, which is just instead of any vectors, just take the elements of the basis of vectors, then I get the components are sigma mu nu, and I can write it in terms of a sum of elements of the basis of twice covariant tensors, which is the tensor product of elements of the basis of one forms, and then I get that the components are antisymmetric, right? Remember, just a refresher, sigma mu nu, the components are equal to the tensor sigma acting on epsilon mu epsilon nu, right? And of course, the antisymmetry implies that if I swap the indices, I get a minus. All right, so let me define a very useful object. Let me define the wedge product. The wedge product is the antisymmetric tensor product. So, what is that? Well, the wedge product of, here I wrote between the wedge product of two elements of the basis of one forms, and I dx mu wedge dx nu, and it's antisymmetric, all right, by definition. And I define it as the antisymmetrization multiplied by 2 to remove the 1/2 factor, the antisymmetrization of the tensor product of dx mu dx nu. Remember this notation for antisymmetrization? This means that this parenthesis, this thing would be 1/2 of all this, and then the 2 cancels the 1/2. After defining the wedge product, I can write the two form sigma in the following way. It's nice because to write the two form sigma, I can write it only as something that is proportional, if you want, to elements of the basis that are wedge products of elements of the basis of one forms. Now you can quickly, something nice to check is this really equal to that? Well, let's see. This thing is sigma, it's equal to 1/2 sigma mu nu, and then I expand this. Okay, so this is dx mu tensor dx nu, right, minus dx nu tensor dx mu. All right, I can separate in two. I get 1/2, and then I get sigma mu nu dx mu tensor dx nu. All right, minus sigma mu nu dx nu tensor dx mu. But now I can change the name of the indices in this command to match these ones because they're dummy indices. So if I do that, let me swap them here like that, and then I use the fact that it's an antisymmetric tensor. So this thing, it's equal to this thing if you want. This is plus sigma mu nu. All right, so with that, I take common factor and I get twice, so I get 1/2 of twice sigma mu nu dx mu tensor dx nu. which is of course the original expression that we had. Okay, so we've learned what the wedge product is. Maybe right now you don't see why it's so useful. It's going to be very useful to handle forms in general, and forms, as we will see. But now you see how this is helpful in terms of, well, I can run forms only in terms of wedge products of elements of the basis of one forms. Right, an n form is, well, we know one forms, two forms, extending it to three forms, four forms, etc. is not that difficult. An n form is a fully antisymmetric n times covariant tensor, a 0n type tensor, that is fully antisymmetric under the change of any two. So if I were to write this is equal to minus sigma, V3, V2, V1, Vn, right? I swapped V1 and V3, and that already gives me a minus sign. Any two swapping of arguments will give me a minus sign. That's what I mean by fully antisymmetric, like the Levi-Civita symbol, if you remember. All right, let me erase that. Now, of course, we have the component. We can write this n form. It's a tensor. We can write it in terms of the basis of tensors, of n covariant tensor, which is the tensor product of the basis of one forms, n times, and these are the components. And of course, I can express the form in terms of the antisymmetrized tensor product, the wedge product, and that gives me this expression. Now I need to divide by the factorial that comes from the antisymmetrization. Now, of course, the contraction with a vector, meaning like I act on one vector and I leave all the other arguments blank, as in like I don't put anything there. By contraction, I reduce. Remember the contraction that we see, what we saw in the previous video? It reduces the tensor nature from, and 0n will be a 0n minus 1 in this case. Now, if I do that, of course, I get this expression here. To get it, it's very easy. Just remember that you substitute on v. You can write this as v mu partial mu, just to write it in a coordinate basis. And then you know that the elements of the base of one form, dx alpha, acting on the elements of the basis of vectors partial mu. Again, remember that I'm slightly abusing notation and representing them with the symbol that we inherited from the mapping to Rn, partials and differentials of the coordinates. This thing is the dual basis of this one, so we know that this is delta alpha mu, and that will give you this expression, very easy. All right, we can also recast this in terms of the basis with the antisymmetrized wedge product in here, and then we obtain this expression. Right now it's the factorial of n minus 1 because one of the elements of the basis is no longer there, as you can tell. Now let me define an operation between n forms that is based on this wedge product that we only talked about it in terms of elements of basis, but we can actually do it in terms of any sorts of forms. Let's see. Let me first, before talking about the exterior product, let me use a shorthand notation for the contraction. Remember, the contraction of an n form with a vector v is, well, take v as the first argument, so apply to one vector, contract the first index if you want with the vector v. And let me just abbreviate that operation as I sub v, where v is the vector, and then sigma. This is a common notation in differential geometry for the contraction. Not super important because in our course we're not going to use it a lot. But in other contexts, for example, if you were to take quantum 3 and learn what really means to quantize things, I think it's important to use this notation, and it's important that you know it, so if you see it in books, you're not surprised. Those of you who haven't seen differential geometry, those of you who have, probably you're used to that already. Okay, so I call this the contraction of the n form sigma with the vector v. Now, if sigma is a k form and omega is a p form, we can define the exterior product, which we usually also call the wedge product, right? Between them, and I notate it as sigma wedge omega, as their fully antisymmetrized tensor product. Now, I give you here the components. I think it's a good exercise if you actually prove this relationship. So knowing that is the fully antisymmetrized tensor product, so get the tensor product that we saw in the previous video, and then antisymmetrize all the indices, all of them, and then you get this. It's an exercise on combinatorics and index notation. So try it, please, and if you have questions, do ask me. These are the components of the exterior product of sigma and omega as a function of the components of sigma and omega. See the fully antisymmetrized here. Now, one question that I sometimes have from people who haven't practiced too much with this before is like, what do you mean antisymmetrizing like that? So if I write a tensor T nu and another tensor R, I don't know, sigma rho, and I write this, what does that mean? Well, that means antisymmetrize these two indices. So this would mean 1/2, and then I write T mu nu r sigma rho minus t, and then I swap these two, so mu sigma r nu rho. That's what it would mean. Okay? All right. Also, here's another identity that I think that, again, we're not going to be using a lot in this course, but it's a very useful one, and it's a nice exercise. I mean, this could be asked in an assignment, for example, to practice index notation. I'm probably not going to ask it in an assignment, but it's a reference of something that could be asked maybe. So this identity tells me that the contraction of the wedge product of sigma and omega with the vector v, it's equal to the wedge product of the contraction of sigma with the vector v and omega plus minus 1 to k, where k is the order of form that sigma is, the wedge product between sigma and the contraction of v with omega. All right, let's define the exterior derivative. All right, we define the exterior derivative. It's an operator d that acts, it's like taking the generalization of taking the differential outside of just on functions, right? That acts on an n form sigma and returns the n plus 1 form. So it upgrades from, from an n form, creates an n plus 1 form that I call d sigma, right? And this sigma is like kind of the differential of sigma, right? Is 1 over n factorial. The differential of the components, remember that this sigma is an n form field. So the components vary with the point, they're functions. The components of the n form are functions. So I can take the differential of the components as it's the differential of a function. So df, right, the differential of the function, which is the partial derivative of f with a bar dx mu, right? So in this case, because the components are coordinate functions, they're functions on R, it's okay not to write the bar. So maybe let me just not write it for now for clarity. So partial mu f dx mu. So yeah, I can write this as partial beta dx beta. You see, it's the same thing. It's substitute, you call f this thing here. This is the f, okay? So the differential of the components, wedge product, exterior product with the differential of the coordinates, right? With the elements of the basis. So this is in terms of the wedge, because it's very convenient with defining with respect to the wedge. We can write it in terms of the standard basis, the tensor product of the basis, to get what the components of the exterior derivatives are, and the components are this. So the antisymmetrization now goes into the components like this, right? It's n plus 1, and then antisymmetrized partial derivative with respect to beta, sigma, alpha 1, alpha n, all the combinations. So the beta start being combined with its sign, the sign of the permutation with respect to all the possible. So it has elements here of all the possible permutations of these indices. Okay, that's why it's so much more convenient to write in terms of the wedge. Right, there's a property that the exterior derivative satisfies, that is the analogous to the Leibniz rule, but it's not quite Leibniz rule with respect to the wedge product. We call it the antisymmetrized Leibniz rule. This is the property that is satisfied. Okay, this thing is the exterior derivative of the wedge product of two forms. This is an n form, and omega is a k form. Is kind of, it would be like the Leibniz rule if that wasn't there, but you need this minus 1 to the n, where n is the n of the n form. All right. I'm not going to prove this property here because in this course we're not going to use this too much, but it's good knowledge that you have. And now what we're going to do is some examples. Let's play a little bit with all this because I think it's pretty abstract as is, and I think some examples will be really helpful. And maybe after this video, you feel satisfaction that you understand better how to do multivariable integrals that you've been doing so far without maybe thinking too much about it. Let's see. Let's begin with the simplest of forms, a zero form, which is a function, a zero tensor, right? So the zero form, what is the exterior derivative of a zero form of a function? Well, easy, it's the differential of the function, right? So if we apply the formula that we have in here, that's very easy, because this thing is 1 over 1, so nothing. It's just the differential of the function. Differential of the function is the partial derivative with respect to, let's call it beta, and then the function. And I don't have indices to antisymmetrize because it has no indices, and then dxb. Then indeed, yeah, this is what we know already for functions. Okay, wonderful. Let's try with a one form. Well, with a one form, omega, we know that omega is omega alpha dx alpha, right? Elements of the basis. So we add the exterior derivative, and we get, based on the components, this expression, the partial derivative of omega, right? And it's very, very easy here because we could have done it many ways. We could have done it directly from here. But let's start from writing the components here, and let's arrive to the original expression. So let's just expand this. That would be anti-symmetrization of these two indices, so 1 over 2 that cancels the 2. So this gives me partial beta omega alpha minus partial alpha omega beta. Right, and this multiplies dx beta tensor dx alpha. I can write this as two summands, so let me do it. Partial beta omega alpha dx beta tensor dx alpha and minus partial alpha omega beta dx beta tensor dx alpha. All right, and now what I can do, as I did before, I can swap the indices, the dummy indices, right? I can make a change. Alpha, I call it Joshua, beta, I call it Peter, then Joshua, I call beta, and Peter, I call alpha. An index swap on the second term. That gives me partial beta omega alpha dx beta tensor dx alpha minus partial beta omega alpha dx alpha tensor dx beta. Keep in mind, this and this are exactly the same. It's a sum on two dummy indices, right? Wonderful. Now I can take the common factor partial beta omega alpha, and that gives me partial beta omega alpha, and multiplies the anti-symmetrized tensor product dx beta tensor dx alpha minus dx alpha tensor dx beta. Right. And now this thing is exactly the wedge product of dx beta dx alpha, right? Remember that dx beta dx alpha was defined as twice the anti-symmetrized tensor product. It would be like this, beta tensor dx alpha, right? And then the anti-symmetrization gets a 1/2 that cancels the 2, so this thing is exactly the wedge product. So what I get in the end is this exact expression here. Because remember, this is a one form, so it's 1 over 1. So I get exactly this expression here. And of course that means, because this is the differential of the components, that means that I get this expression as well. All right, as an exercise, I hope that this was easy to follow. As an exercise, please do the case of the two form. And do it like I did. Start from the components and prove that you can express in terms of the wedge product. This is a good practice if you've never done it. Let's see one more thing. All right, let's talk about closeness and exactness. Closed and exact forms. So the definition are easy. A form omega is exact if it's the exterior derivative of another form. Okay, I can write omega as the exterior derivative of sigma, being sigma another form. A form omega is closed if its exterior derivative is 0. So if I take the exterior derivative of omega, it's 0. Now, how do they relate with one with another? Okay, this one is very powerful. A form that is exact is closed, always. A form that is exact is always closed. Now, the opposite is not true. A form that is closed is not always exact, but it's true locally. So a form that is closed locally implies that it's exact. So if you're looking at a form that you are in a part of the manifold, around a point of the manifold, and in that part of the manifold, the form happens to be closed, then in that little part of the manifold is exact. Now you have to be careful because there are implications on this statement when you integrate, for example, and when the integrals are on domains that cover more than a local region. So that's why you need something else in order for closeness to imply exactness, which is the Poincaré lemma. Is the domain of the form contractible? If the domain is contractible and the form is closed, then it's also exact. I'm not going to tell you more because there will be an assignment that hopefully you have fun with. And this is something that maybe in thermodynamics, when you saw thermodynamics, the professor maybe told you a little bit about that. Okay, let's do an example with a one form. We're going to see several things. We're going to show, with this example, we're going to illustrate that the square of the exterior derivative applied twice will be always, it's like the zero operator. We will return a 0 when applied to any form. And we're going to relate it with things that you've seen in thermodynamics. Now, you see, if omega is exact, that is kind of nice to integrate because I know in mind that omega is a one form. If it's exact, then I know there is a function, which is a 0 form, so that omega is the exterior derivative of that function, is the differential of that function. Then integrating is easy. It's just, it doesn't depend on the trajectory. It depends only on the starting and final points. It's like internal energy in thermodynamics. All right, let's see what the conditions are for omega to be the differential of a function. Let's compute the differential of f again. The differential of f is, of course, equal to partial mu f. Let me just abuse not write the bar there. Partial mu f dx mu, right? So I get the partial derivatives contracted with the elements of the basis of one forms. Please allow me the abuse of not writing the bar here. We know what we're talking about. So we see here quickly that the condition for omega to be exact is, so omega exact means that omega alpha is the partial derivative of a function. All right, those are the components. This is omega, of course, the one form, and these are the components. All right, let's compute the exterior derivative of this form now. So let's compute the omega, right, which is d df. All right, and if what I told you is true, that has to be 0. Okay, so let's compute. Now we use the definition that we had from before. That's going to be the differential of the partial derivative of f, okay, now wedged with dx mu. All right, now what does that mean? All right, so taking the differential of this is taking the partial derivative nu, a different index now, and I get this partial mu f, right, dx nu. That is the differential of this expression. Now, that is wedged with the x mu. But this is particularly interesting, right? Because this object is antisymmetric, remember? Dx nu wedged dx nu is equal to minus dx mu wedged dx nu. So if I swap the indices, I get a negative sign, right? And this thing, is this thing antisymmetric too? No. This thing is symmetric. And something symmetric, well, if you satisfy the cauchy bars inequality for the function, so if partial nu, partial mu, f it's equal to partial mu, partial nu, f, if this is true, then this object is symmetric. And we have a contraction of something symmetric with something antisymmetric, that will give me 0. Hopefully you see, of course, this condition has to be satisfied, but this condition is true for smooth functions in the manifold, right? Because we said it's class infinity. For a class infinity function, you satisfy always this condition. So this is exactly 0. You want to see it in a particular case. For those of you who are not that used to the abstract notation, but you should get used to it, we can do it in the case of, I don't know, a two-variable function, for example, dimension 2 manifold. So let's just write a dimension 2 manifold. This would be partial x, partial y, with y and x being the variables, right? F dx wedge this is nu, yeah, dy, plus partial y, partial x, dy dx, right? X being x1 and y being x2. And of course you see that this is equals to partial x, partial yf, minus partial y, partial x, f. I switch these two to have the same element here, and that gives me a minus sign here that I put there, dx wedge dy. And you see that this is 0. If the partial derivatives commute on the function, that is 0. And they do. All right, wonderful. So we see how, indeed, this is a practical example, if you want, of a one form that is exact and is closed. Now, let's revisit multivariable integration as you saw it in your calculus courses, and let's see if there's something fishy in that thing that you learned that we can understand better now. All right, so remember that we were able to do line integrals, or recast line integrals as the integral of a one form, right? Now, of course, you can integrate any n forms, and you will. There will be an assignment exercise about that. And that would correspond to what you've seen in vector calculus as volume integrals, surface integrals, and so on. This is the generalization of those concepts. Now, let's revisit something that in calculus you haven't seen like that, probably. And also something that I get questions sometimes that confuses people a little bit. Let's go to the simplest change of coordinates that you can think of when you were integrating something. Say that I have the integral of 1 in some region, in Cartesian coordinates, right? But then I changed to polar coordinates. And this is the change of coordinates, right? And you know that the change of coordinates is under the integral sign is like this, where r comes from being a Jacobian, right? All right. Now, let's do something here that not everybody, but some people find like, oh, hold on, what? Let's see. So if I compute the differential of x, I can, right? I can compute, it's very easy to compute the differential of x. We even know in differential geometry how to do it, right? Partial derivative with respect to the variables times the differential of the variable, as I have first one and second one. And same for y, I differentiate y and I obtain this. Now, if I now multiply, as this notation seems to suggest, the multiplication, dx times dy kind of thing. If I multiply the two, what do I get? Well, I get this. I get this expression. And this expression is nothing like, this is the important bit, dx dy is certainly not r dr d theta. So then, what the heck are we doing here? Shouldn't it be, and I know that you may know the answer, but shouldn't it be that this is the, if this is the product of dx dy, then this should be the product of the two dx and dy that I computed. How come it doesn't work? Aha! Well, the answer is because this is not the product. This thing is representing a volume form. The volume form of R2 in that case. So this thing, what you are actually doing is the integral of dx wedge dy. Do you believe me? So there should be a wedge in here, just nothing indicating a product. But then we don't write it. Do you believe me? Let's see what happens having dx and dy, and what happens when I compute the product of dx wedge dy, the exterior product between these two one forms, okay? The x is a one form, the y is a one form. I can build a two form computing the wedge product between the two. Let's do it. All right, so let's see what we get. So if we compute the wedge product of these two one forms, we get, well, this times this one is linear, right? So this times this one, what I get is this, cosine sine dr wedge dr. Then I get these two, right? So r cosine square dr wedge d theta. Then this one and this one, r sine square theta d theta wedge dr, and finally minus r squared sine theta cos theta d theta wedge d theta. Now, what is the wedge product of a form with itself? Well, the wedge product is antisymmetric, so that has to be equal to minus omega omega, and of course that means it's zero, right? If I write like that. So I know that the wedge product of dr with dr, this is zero. I know that this one is zero. And now look at what I get, let's just write it, r cosine square theta dr wedge d theta, okay, minus r sine square theta d theta wedge dr. And now I can use the antisymmetric property to write this one as, this one is of course, let me write here, it's minus dr wedge d theta, right? So I can write this common factor, r that multiplies cosine square theta plus sine square theta, then dr wedge d theta. Oh my goodness! R dr wedge d theta. So, that's the right Jacobian. That's where the Jacobian comes from. Remember the change of coordinate basis is Jacobian matrix, so this shouldn't be surprising. That you get that. I mean, you saw it as a determinant that you get in there, but of course you get that determinant. The antisymmetric nature of the tensor together with the change of basis. This is the determinant that you get. I just computed, you should be able to compute the differential dx, the dy, and the product of the two to find the volume form, but the right product. This is not a product per se. This thing is certainly a wedge product. People don't tell you, but in calculus, but this is a wedge product, and that's why it's funny that if you do it like that, you don't get it, but if you do it properly, you get exactly what you want. All right, so you see how what we see in differential geometry also can teach you about vector calculus that you knew from before. Wouldn't it be nice to be able to explain the change of coordinates in multivariable calculus like this with the language and power of differential geometry? I think so. Well, I think this is also enough for this video. In the next videos where we're going to see smooth maps, pullbacks and push forwards, and we're going to see diffeomorphisms. Until then, take care.